Welcome to Investigation 1.3, Writing an Equation. In this investigation, we're going to be focusing on how to write an equation for a quadratic form, or for a quadratic function, and we're playing around with the concept of having one variable instead of two. So if you think about the area equation for a rectangle, we're talking length times width. Well, we are going to learn today how to rewrite width, so that way it doesn't have a W in there. We're not looking at a second variable, but instead we would maybe write the width as a number that's in terms of the area. So our focus question is, how can you write an equation for the areas of a rectangle with a fixed perimeter? So here's another little hint. We're going to be looking at perimeters as well to be able to find our areas. So let's come in here. We have a situation where we have a rectangle. This rectangle has a perimeter of 40 meters. Awesome. Every rectangle we're going to talk about will have a perimeter of 40 meters. So our job right now is to do a couple of things. To start out with, let's talk about the area equation. Area is equal to length times width. Cool. Awesome. Perimeter equation is essentially the space around the edges, so we have essentially two lengths and two widths, and we're adding them together, so we have 2L plus 2W. We could also write that as 2 times L plus W, depending on how you want to think about it. So our first step in this problem is to do this. We need to label one side L for length, so a cursive L. Whoop, there's our cursive L for length. And we need to label the width in terms of L. So instead of writing a W, we are going to be writing something else. And it's not going to have a W in it. We're going to say the width is equal to the length somehow. So we need to think about the perimeter and area and rewrite this equation, or rewrite these sides. So instead of writing width, we need to write something different. If we look at our perimeter, we have 40 meters. So our perimeter is equal to 40 meters, and that is two sets of our length plus our widths added together. Two sets of it. So that means if I wanted to look at just one set, like this one, or maybe this one, we are looking at 20 meters is equal to the length plus the width. So that tells me that I can rewrite my width equation, or my width, as saying 20 minus my length. So if I have this part right here, oops, I'm not going to use that color. If I have this part right here plus this part right here, I get 20 meters. And if I were to just subtract this length from that 20, I would get my width. So I could say my width is equal to 20 meters minus my length. Hope you're picking up what I'm putting down. I'm going to rewrite that L so it's a cursive L because that's what they want us to do. Write it in the cursive L. So another thing we could say is we could make an equation for our area and say our area is not just our length times our width, but it's our length times our width, which is 20 minus L. Hope you're picking up what I'm putting down right now. So I just replaced that width with 20 minus L. So essentially getting rid of that second variable. So what's interesting about quadratic equations and equation solving in general is however number of variables you have, say we have 3 variables in an equation, maybe a k, a t, and an r. That means we have to have 3 equations to be able to figure out what all of those variables mean. So if I have one equation and I only want to have one thing I don't know, one thing. As of right now, we don't know our length. We don't want to not know our length and our width if we know our length, we would be able to solve for the area, which is kind of nice. So our next part of this is to make a table for our equation to show the relationship of the length and the area. So let's rewrite our equation so we can see it. Area is equal to length times 20 minus L. And we're going to move over so we have a little bit of space and we can actually create a table. So we need to make a table for this situation. We have a perimeter. We also want to remember we have a perimeter which is equal to 40 meters. That's going to be important. So let's think about a couple of rectangles. Let's start nice and easy. If I have a rectangle that has 1 meter on the side, it's 1 meter wide, how big does the width need to be to make a 40 meter perimeter? Well, if it's 1 meter on one side, that means this other side has to be 19 meters, because 1 plus 19 equals 20, and that's going to be reflected on the other side, so we get 40. So our width would have to be 19, so that means our area, 1 times 19, would be 19 meters squared. If I had doubled my length, so now it's 2, that means my width has to be 18. 2 times 18 gets me 36. And we're going to fill out this whole table, so bear with me, I'm going to do a little math magic. So, little math magic. So now, as I look at this, I can start to see everything forming. We're starting really small. We're getting bigger and bigger and bigger till we get to 100, and then it decreases again. So it's going down here, and it's heading up here. So we have kind of that mirror image is happening right here at 10 with an area of 100. So there's our relationship with all of that. If we think about it, we can start to see how everything's forming. So essentially, I'm going to add a little bit more math in here. To see the area, the length and the area, I had 1 times 19. For 2, I had 2 times 18. For 3, I had 3 times 17, and so on. And so you can kind of see how this 1 became 10, and then from there, everything began to flip-flop and meet towards that middle section. So here's our next step. We need to now sketch a graph of the relationship between the length and the area. How can we use our graph to find the maximum area possible? And how does your graph show how the length corresponds to the maximum area? So we need to do a graph. If I look at my graph, I don't really like the graph I chose. So I'm going to modify it a little bit. I'm going to say this is my y-axis. And this is my x-axis. Is that okay? I think we can handle it. Breathe. It's all right. All right. So let's also get this table in here so we can see it. Ooh, don't screw with me. There we go. So there's our table, and there is our graph. So looking at this, we want our length to be along the bottom, and we're going to look at area along this side. So let's do a little breaking up of things. If I look along the bottom, I have 20 spaces, which is awesome. That's exactly what I need. So each one of these is going to be equal to 1. So we're going to go all the way across, all the way up to 20. Awesome. And if we go up to the top, we also again have 20 spaces. So each one of these I'm going to say is equal to 5. It's always helpful to find a scale that works for your data, so that way you use as much of your graph paper as possible and you're utilizing it well. So all the way up. So all the way up to the top, and then we have 100. So this middle section is 50, and so on. So I'm going to do a little math magic, and I'm going to graph it, and then we'll talk. So a little math magic. If you can see very faintly, I've added in our parabola. So I'm just going to connect some dots. Whoom. Whoom. So we can now see how that parabola is really growing up and becoming beautiful. It's growing wings like a butterfly, not really. All right, so we need to sketch a graph of the relationship between the length and the area. Check We've done that. Now how can you use your graph to find the maximum area possible? The maximum area possible we can see in that little hump at the very top. We can see where it hits its peak. Essentially, the maximum area possible we know from our table is 100 meters squared, so we can see it right there in that table, or the graph as well, as being that peak, that hump, that top of the hill. And then also, how does our graph show the length that corresponds to the maximum area? If we were to follow this down to our x-axis, we would be able to say, oh, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So at 10 meters by 10 meters, we'd be able to find that max area of 100 meters. Awesome. I hope this information helps. I hope you enjoy watching this video, and good luck with investigation 1.3. Bye.